very excited to be here to tell you about kuibit, this package for post-processing simulations with Cactus code bases. It's late, and I will try to keep this light and fun. But you all help me. I want this to be interactive. So let's see. So first, I want to tell you what I think is the ideal audience for this presentation. I'm talking to you. I'm talking to the people online that I'm accepting right now. But I'm also talking to everyone that's going to watch this recording in the future. And I think the ideal person that will benefit the most from this talk today, this tutorial, is someone that has started working with any kind of Cactus-based code. So Einstein toolkit, the old Illinois code, whatever. And you want to learn what's inside your simulation. You want to post-process your simulation. You want to do some analysis. So this is what I'm planning to do today. And again, I'm going to ask you to help me, and you'll see what I mean in a second. So first, I want to tell you about kuibit in general, and to give you a general introduction about this package. Then I'm going to show you how to install kuibit and do some little bit of setup to get the most, I think, at least in my opinion, with kuibit. Then I want to show you some examples of how you can get some interesting results, some interesting movies, plots, without writing any code, just using the examples that are bundled with the Einstein toolkit. And then, since we have a lot of time, I think it's going to be good to take a small break or take more questions if there are any questions. Finally, I want to try to do live coding. So my idea here is, let's build together something that is not available in kuibit, something that uses kuibit, but it's not something that you get out of the box. So you can see how I think about kuibit, what is my reasoning behind how I structure my code. And you can help me by asking questions. I use kuibit a lot. I spend a lot of time with kuibit. Everything is clear to me, well, I hope. But I'm sure it's not the same for you. So I want to make sure that every one of you can understand what's going on and can explore those areas of kuibit that maybe I give for granted, but maybe they're not so easy to understand or so clear. So please ask questions. Tell me what happens if you do that. What happens if you do this? And everything that you're going to see today, all the slides, all the codes, everything is going to be public. It's already available on this GitHub repo. So I don't think you have to follow along. If you want to follow along, please do so. But I'm asking you, just pay attention what's going on and ask questions and interrupt me. And I'm very, very happy to have a discussion as opposed to 2 hours of me talking. So please don't be shy, ask questions. I really want this to be interactive. I really want to make sure that I explain everything that I think it's obvious, because for sure it's not obvious. Okay, so this is my plan for today, and I hope you can help me make this successful. So let's get started with one. One is, I want to give you a general overview of kuibit. Well, what is kuibit? Kuibit is a Python library for post-processing simulations. So what I mean with post-processing? Well, I think there's two sides of post-processing. On one side, we're just making cool visualizations like what we have here on the left. There is a equation onto binary black holes. We're looking at the rest mass density. I think this is pretty. It's useful to see what's going on, but this is not something that you can do like quantitative analysis. This is just something that you do to get a sense of what's going on, or to put in your talk like this to impress people. But with kuibit, what you can do is you can really go down and do like a full quantitative analysis as if you're running your code with your Cactus simulation. So you can do any kind of like post-processing, crunching numbers, or any kind of, a lot of post-processing for quantitative answers. For example, here we have on the right, we have our gravitational wave signal. This you can use, you can put in a catalog, you can do whatever you want. This is it's a good answer. It's not just qualitative description of what happens. And this is what I mean with post-processing. And the goal of kuibit is, I should steal the slogan from the black hole perturbation toolkit, that is to reduce the time spent writing code and increase the time spent doing science. Kuibit wants to take care of all the low-level details so that you can focus on your science. ignore all the technicalities with headers, HTML files, and file structure, whatever. Just do your science. And in this, what I really care about also is lowering the entry barrier to do science with Einstein Toolkit or Cactus-based simulations. And to give you another example of post-processing that you can do, quantitative post-processing you can do, I have written a full ray tracing radiation transfer code from Einstein Toolkit simulation data. So this, if you're familiar, this is solving ordinary differential equations to get black hole images similar to what the Event Horizon Telescope does, but with Einstein Toolkit data. So this is something that is just visualization. Question?
Just a quick question. What's the license on kuibit?
As GPL3 or later, yes. Okay, so in this talk, I'm not going to tell you about all the motivation, all the, I'm not going to give you an introduction. I want to have a hands-on point of view. I want to show you how to do things. But there's a lot that goes behind the scenes, or in terms of like design, in terms of ideas, in terms of what problems kuibit is trying to solve. Especially if you haven't worked with Einstein Toolkit without kuibit, probably are not familiar with the pain that it takes to do some like a complex visualization or post-processing. So if you want to learn more about that, I encourage you to just Google kuibit on YouTube. I don't know if it's a verb, kuibit on YouTube. And there's videos from previous Einstein Toolkit schools. There's videos from seminars, and there's other videos that you can watch to have a better overview of the project and the motivation that led to this project. So I'm going to focus on something else today. Let's see what I have next. Yes. So I think the first step when using a new software is, how can I get help? How can I get started? So what I want to really emphasize with kuibit is the documentation that's available and how you can get the most out of kuibit. So I like to split documentation in 4 different parts. One is how to use different modules. That is, in this case, I'm showing an example of the SimDeer that we're going to discuss today later. Then there's tutorials that teach you how to get some stuff done. Then if you're a programmer and you're probably going to use, you probably want to use fundamental functions and structures provided in kuibit. So you want to have access to all the APIs, application interfaces, programming interfaces, but also examples on how to get stuff done. And again, this is different from tutorials because examples are, completed codes that achieve some goals. Tutorials just are a pedagogical way to show you something. So this is how you can get started. You look at the documentation first before even downloading the code, because the documentation tells you how to download the code, of course. But probably the documentation is not enough if you want to get some stuff done with kuibit. You want more. Well, in that case, you can get help. And there's at least 3 ways you can get help. One, you can send me an email and I'm going to answer. Typically within 24 hours if I'm not in the mountains. Or you can join this Telegram group that involves kuibit users and developers. That is me in this moment. You can ask questions there so everyone can see the answer. Sometimes it's useful for other users to see how to solve some problems. And finally, you can come and chat with me. I'm very, very happy to help you get stuff done. Whatever is your need, I want you to reach out, and I want to support you in achieving your goal. So I'm here tomorrow. If you want to chat, I'm available. If you want to set up a Zoom call for later, we can set that up. So this is how you can get help. You look at the documentation and you ask someone that is me, probably will help you. Okay, so there's something I want to emphasize about what is kuibit, because this will help us in the later hands-on part of this tutorial today. I want to tell you about the structure of the project itself. So at its core, the most important part of kuibit is the Python module. So import kuibit. And mentally, I decide that kuibit is split in 3 different parts: what I call objects, what I call readers, and what I call utilities. I'm going to describe these later, but fundamentally, objects are high-level abstractions that help you wrap your head around some fundamental structures. For example, you don't want to think about time series as one array with a second array, but then when you do some operation, you have to make sure that things are synced. You just want to think about one time series, whatever that time series is. Readers is what interfaces your simulation data with your objects. And finally, utilities, which are, well, we're going to see what utilities are. Second, we have all this documentation. The documentation is online, website that I showed you earlier, but also documentation that is inline. That is, if you open the code, there's a lot of comments. You can extend the code if you want or if you need to. So this is an important part, I think, of the project. Is all the documentation that comes with the module itself, and also all these examples, which I'm going to discuss in that later. Well, those are modules or codes that you can use immediately to do science. If you want to make plots, you don't have to write anything. Those are very useful pieces that are built upon on top of the module, but they're not modules themselves. Finally, there's a lot of infrastructure to ensure that everything works and keeps working. Continuous documentation, continuous delivery, continuous documentation. Every time there's a new commit, everything is tested, everything is linted, everything is deployed, and so on. And I also, yeah.
Speaking of testing and linting, when did it fail?
Yes, it fails. It fails because of BTK, but we can discuss that later. I'm aware of that. Yes, it's not a big deal. Yes, and I also like to think that kuibit is like other value that kuibit has is the know-how. If you want to learn how to move from Psi4 to your gravitational strain, you can read the source code in kuibit. And if you want to implement this in Julia or in your favorite language, this is an example that you can take, that you can look at if you want to get something done. So, or if you want to glue together all these different pieces, how to use carpet without looking at carpet source code. So this is how I think about kuibit. And this design is, one of my goals with this design is to ensure that kuibit is workflow independent. I don't want to write Jupyter notebooks. I don't want to write skips. I don't want to write GUIs. You do whatever you want. And this, to me, is probably the best way to ensure that anyone uses the workflow that they prefer. I prefer writing scripts, but you can do whatever you want. And I want kuibit to be able to support you in the workflow that you prefer. Okay, so this is how I think about the fundamental structure of kuibit as a project and the modules. But for better understanding what's coming soon, I want to zoom in for a second in this object readers utilities and tell you a little bit more so that you can find yourself, you can move a little bit better in the code base. So first we have these objects. Again, objects are high-level abstractions that help you forget about the details. So you can work with time series, which means that you don't have to work with like separate arrays. You don't have to stitch things together. You don't have to, you just think of a time series in the same way as a physicist or a mathematician. You think about like a series, like a function. Same with frequency series, or we have like grid data. Again, grid data can mean many things. And if you want to keep track of all these different arrays, it becomes painful. So these high-level objects are a way for us to essentially forget about the low-level details. Next, we have readers. Readers are all those modules that interface the data that you have on your hard drive with these objects. So readers are a way to organize the content of your simulation in such a way that you can be presented with an object. So readers are just a way to, again, serve you with something that's high level and that you can use immediately. And finally, we have utilities, which just implement some physics or some useful software engineering aspects like visualization. And as you see, to me, visualization is not the core of kuibit. It's just something that comes at the end because it's useful to visualize stuff. But the goal is to be able to do post-processing. And so let me describe a little bit better all these modules. So some examples of utilities are some gravitational wave functions. Here, the examples I have is to move from luminosity distance to redshift, compute antenna patterns for the various detectors, or sensitivity curves of the available detectors, working with units, which, especially for beginners, is typically very confusing, computing mismatches. But also, I have an arc-parse helper to help you write command line scripts, or there's a module for visualization with a matplotlib. So these are utilities. And next, we have objects, which I already described, high-level interfaces that implement useful abstractions. So here are the examples I'm showing is that this time series, I can just evaluate the value of 10. I don't need to bisect and find what is in the array, what is the time 10 and find the corresponding value. I have just a spline that represents everything. Or I can do mathematical operations on this time series without worrying about the underlying data structures. Time series implement, again, this high-level interface. And same will work for grid data. You can just do any mathematical operation. You don't have to think about all the low-level details. Then we have uniform grid data that represent data defined on a single patch with uniform resolution. So this can be a refinement level. This can be one part of an MPI rank. And then we have hierarchical grid data, which puts everything together so that we have essentially fixed or adaptive mesh refinement. And at the end of the day, it's just a collection of uniform grid data. And something I want to remark is that you cannot visualize directly hierarchical grid data. If you want to make visualization, you have to resample to uniform grid data because it doesn't make too much sense to have multiple resolutions on a single image. So this should be kept in mind. As for readers, well, once again, the goal of readers is to organize the data, find what's available, and present you with the object that you want. So readers do a lot of hard work. They have to understand what files are available. They have to read the files, find the metadata. Typically, Joe saying that there's could be 60% regular expressions because there's a lot of header scanning, understanding what's available. And in this, they also try to clean up some data. Typically, we have multiple simulation restarts. Sometimes there's overlapping segments, sometimes no. But we don't want to think about checkpoints as separate entities. We want to have something that is like continuous. And again, this goes once again towards the goal of reducing the low-level details. So this is what readers do. And typically we have three levels of readers. We have main point of entry, which is similar, and everything that's as a dir in their name, as an object type, interfaces with similar. Then we have everything that starts with all. Typically is a dictionary-like object that indexes different grid functions or time series. So all means that the keys typically are grid functions, let's say, so variables. And then one, it means that it's a single, say, grid function, but maybe multiple iterations. We're going to see this in more detail, but I want to emphasize that this is levels. Yes.
Just a quick question. So when you migrate from hierarchical grid data to uniform grid data, does it work in a similar way to your example with the time series, where you say, okay, I wanted a time 10. When you do that, and it does a spline or something automatically. Sometimes I don't want a smooth function going over my data. How does it handle?
So by default, I think it just finds the data, like it treats everything as blocks, and so it's a zero-order interpolation essentially. Okay. But you can also have multilinear resampling. So it's a first-order multilinear interpolation, and this is what the resample or multilinear resample options. So by default, also for computational speed, it just copies the data like the closest point. Okay. Yes, nearest point. Thanks.
I got you.
And something else I would like to emphasize is that all these objects behave like dictionaries. So they have keys. And if you print them, you typically understand what's inside. So if you don't know what happens, ask the instance what type is the object I'm looking at and print it, and something will pop out, and you'll probably know what to do next. Okay, so I think I'm getting closer to the end of my introduction. So I think kuibit is a very nice way to share code because it's very easy to abstract away all the low-level details. So if you have a useful script to do some post-processing, I think you can port or use kuibit so that it doesn't matter what's the underlying data. It can just work and you can share with other people. So in the same spirit, an Einstein toolkit has all the thorns and we can achieve more by sharing. I think kuibit can be the same, but for post-processing. And it's completely open. It's GPL 3 or later. I hope it's well commented, well developed. I hope it's easy to extend. And there's a lot of software engineering that goes in kuibit. Here, maybe summarizing something in this Cactus. So I'm very happy to help people contribute to kuibit and learn along the way. Yes.
Do you have off the top of your head, what are all the dependencies that kuibit has on other Python packages?
Okay, so there's a lot of dependencies, and they're all listed in a TOML file. And I can.
I'm imagining HDF5.
Yes.
NumPy.
Yes.
Matplotlib.
Well, matplotlib, yes.
Is optional, or is
well, if you don't use the visualized matplotlib plot, you don't need it. But yes, so the hardcore ones are yes, NumPy, SciPy, H5Py. But then there's many more. Like maybe there's a list of 10 and all the dependencies of the dependencies. So at the end, it's like many dependencies. It's I'm not
we
going.
might have many of them installed already, but
yes, but there's also some features which probably should be optional, but since I use them, they're mandatory. so yeah, but yeah, we can look at the dependencies if you're interested. And again, maybe we'll have a look at the repo later. But if you have some codes, if you want to contribute, please do so, and I'm happy to work together to get your code upstream. So final remarks. So kuibit as a project is published in the Journal of Open Source Software. So if you use it, I will very kindly ask you to cite it. And once again, if you want to get some help, you can either join this Telegram group or you can send me an email. And the name kuibit is a Tohono word. Tohono is the indigenous population around the area of Tucson, Arizona. This stick that we can see in this picture that was traditionally used to pluck the fruit of the saguaro cactus, which, by the way, right now, as we speak, this is the harvest season for the cacti. Fortunately, I'm here, but people back in Tucson are right now harvesting the fruit. So my slogan with kuibit is that you can use kuibit to harvest the fruit of your cactus simulation, the same way people. So okay, before we move on, I would like to give credit to where credit is due. So kuibit grew out of post-Cactus and a package developed originally by Wolfgang Cashdown. It's a complete rewrite, but a lot of the insight that Wolfgang had, since the code was completely open source, ended up being inside kuibit. So the overall structure and design takes a lot from post-Cactus. And of course, kuibit wouldn't exist without the scientific ecosystem in Python, primarily NumPy, SciPy, and H5Py. And of course, all the agencies that gave me money to make this possible, particularly the Texas Valley Center for Computing and NASA that gave me fellowships. And this was my general overview of kuibit. So this was my point one, I think. So if there are no questions, I'll probably move to point two. Point two is setting kuibit up and installing in the opposite order. Okay, I don't see any question. So we can move to setting kuibit up. So if you don't know what to do, you look at the documentation. Here I'm linking two links, but you can also just Google kuibit. And if you Google kuibit, you can go to documentation. And if you help me, maybe my logo will be the first result in Google Images. So, so this is the documentation. And as you see, there is a tutorial, usage pages. It's a long documentation. But you probably want to start with first steps with kuibit. So new to kuibit, first steps with kuibit. So this page walks you through what you can do if you want to start using kuibit. And again, this is my point of view. You can do whatever you want. So this is how I would approach the problem of learning how to use kuibit. Well, the first step is probably to install kuibit. Or maybe, well, you want to check if you already have kuibit. To do so, you just try to import kuibit in your Python interpreter. But if you don't have that, well, you can install kuibit. And to install kuibit, it should be quite easy. It's pip3 install -u, that stands for upgrade kuibit. Now, probably you already have kuibit, yes. And here you can see some of the dependencies. But if you didn't have kuibit, this should probably install kuibit on your computer. And if you're expert with Python, you can use virtual environment, you can use whatever you want. I don't use them, so that's why they're not in documentation. But again, this is a possible way to install kuibit. Since kuibit is available on PyPy, it should be easy to retrieve in different methods. Once you have kuibit, well, let's check that indeed we have kuibit. So I'm going to open a IPython session, and I'm going to try to import kuibit. Okay, I didn't get any error, which means that kuibit is available. Yes. Yeah, I don't know if Conda somehow can access PyPy data, then yes. If not, then no. I've never used Conda, so I don't know how it works. I don't know if you have to package specifically for Conda, or you can get like the standard Python package index system.
Right. I think Conda is going to solve the but the PyPy only tracks Conda.
Yeah. So the dependency issue in with kuibit, they're solved up by poetry. It's a completely different system, and I declare specifically all the dependencies that are allowed. So this is a newer system. I mean, we can go into detail a little bit if you're interested, but so I have so this is what kuibit looks like. Here I declare all my dependencies. So we have numpy, we have optionally numba, we have optionally, well, these are for testing. And then we have some stuff that I sometimes use, so that's why it's here, but technically it's not really needed. And what happens is that I get a log file with all the possible allowed packages. So kuibit is very stable when it comes to dependencies. There shouldn't be any possible way to mess up things unless some packages mess up things upstream, which happens sometimes, like with PyCBC. Okay, so this is installing kuibit with just pip install. And next, I think if you want to take the most advantage of kuibit, it's useful to set some environmental variable up as well. If you have the Einstein toolkit, then you also downloaded kuibit and you downloaded the examples that come with kuibit. So if I go to my Einstein toolkit folder, there's a utilities, there should be a utilities somewhere. Yeah, utils directory. And if you go inside the utils directory, there's an analysis kuibit examples folder, which has two folders, bins and mopy movies. So bins stands for binaries. This is a folder that contains a lot of scripts. These scripts are ready for you to use. So these are the examples that are listed here. So all these examples, most of these, what they do is they make a plot, and they don't depend on anything. You can use whatever folder structure you have, and we're going to work with this example in a second. But I find convenient to ensure that this specific folder here, documents, codes, Einstein toolkit, blah, 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 is in my shell path, so that I can call these scripts from anywhere. I don't have to provide the full path. So what I recommend is that you customize your path variable in your shell so that you can access easily this folder, and you can just call, I don't know, plot 1D, blah, blah, blah. And so in this topic, let me tell you a little bit more about the examples. Once again, examples are codes ready to use, and they achieve a specific goal. I don't know, like plot constraints. You can probably guess that what plot constraints does. Plot constraints plots a given reduction for the constraints, Hamiltonian momentum, and so on. And in the documentation, you can find the code that you can use if you want as a starting point to implement your own script, or you can just run as it is, which is what we're going to do in a second. So these examples are scripts. They use kuibit. If you have kuibit available, you can just use them and get something done again. The second directory that we have here is this mopy movies. Mopy stands for motion picture. It's another utility to make animations with Python. Motion picture, the idea is that you provide how to draw one single frame. You provide how to, you tell motion picture what is the frames that you want to plot. That is your iteration, your time step. A motion picture does everything else to make the movie. So it loops over all the different frames, parallelize everything. It puts everything back together into a single file, and it also cover options. kuibit, Einstein toolkit comes with a couple of movies, actually one movie, that is Grid, which we're going to run in a second. to make a movie of a 2D snapshot or 2D slice of a given grid function. And in the same spirit, sometimes it's useful to have motion picture already. If motion picture knows where to look for movies, that's a little bit easier. So you can customize the second variable, which is mopy movies here, providing the full path of your example folder, so the motion picture would know where to look for. And we're going to see what I mean in a second, if this is not particularly clear or not. And with this, I mean export, blah, blah, blah. Here we'll do like documents, whatever I have to write, like documents. I don't care. So all of this is described in the first steps, I think. I'm pretty sure. Yeah, first steps. Here, this test out examples and recommendation on how to use the examples. Here, get examples, set up the various paths. And finally, as we're going to see, all these examples come with a lot of flags, way too many to remember. And you can always plot constraints, use the help function to learn about all the various flags. Or you can set up top completion so that you get, let's see if it works. Stuck, yeah. You can get top completion for the various flags. Sometimes it's useful, not necessarily needed. And the setup can be annoying depending on your shell. So this is how to stack with it. Fundamentally, you just have to do pip install, but I recommend setting up all these additional variables to make the experience a little bit smoother. But again, it's up to you. Okay, questions? Okay, I don't see any question. So I'm going to move on and I'm going to show you a little bit more about all these examples and what I mean with examples once again. So for that, I have a small data file with some binary neutron star data. So let me go back to my folder. Okay. So if you clone this repo, you're going to find a tinybns.tar.exe. And this contains a very, very small data set for a binary neutron star merger provided by Pedro Espino. Thanks, Pedro. So if you want to use this data, you first have to, is the font big enough? Like the font size? Yeah. Okay. You first have to open the archive and decompress it with xvjf. J stands for.
Can I ask a quick question?
Yes.
So I actually can't open like the examples folder downloaded with Einstein Toolkit. Is there anything else you're supposed to do? You're saying it's not a directory for me.
Yes, it should be a symbolic. Maybe you have to put a trailing slash.
No, it's not a big deal. I'm just wondering if I needed to.
Okay, we can look at that
We can
together.
look at it later.
Yes.
Okay, thank you.
So if you open extract the archive, you're going to find a new folder called tinybns. It doesn't matter what's inside. It's just a collection of files. But we're going to use this folder for our examples. Okay, so since my examples are, my shell knows where to look for my examples, I can plot some of them. And I made a list of the examples I want to show you. So let me open it. Okay. Well, okay. So first, let's plot a grid variable. So you run your simulation. You want to know what it looks like. What's your density? So for that, you can use the plot grid var function or variable or examples. Once again, you can look at the help to see what options you can pass to this script. There's lots of options, but the most interesting ones are probably the most basic ones that are, variable. Well, variable is what you want to plot. In this case, I want to plot the density. This is the rest mass density. Then you want to specify what region of your space you want to look at. This is specified providing the what I call origin and corner, so the lower left and the top right corners of your region. So shorthand is x0, and I'm going to say -20, -20. The top right corner is, I'm going to say 2020. Oops. I personally like to have verbose output. So this -v is just to plot some messages. And as we were discussing before, you cannot plot directly hierarchical grid data. The simulation was run with adaptive mesh refinement. So you have to resample. And this resolution parameter controls how you resample, how many points you want between -20 and 20. So let's just say 300. By default, we're going to do nearest neighbor interpolation. Then since we're plotting density, I'm going to plot with log scale, and I'm going to add a color bar. You run this, and it runs. There's some messages that says, okay, I found these variables. I am plotting this. I'm using this iteration in this region, and that's it. Okay, so where is this? So if you now look at your folder, you're going to see that you have a new file, rowb_xy.png, which we can open. And this is what it looks like. So, and as you can guess, this is completely general. You can plot anything you want. You can plot any variable within any range. You don't have to write any code. And by default, the latest iteration available is used, but you can change that, of course, if you want, with the flag --- iteration. So this is a useful one.
Can I see the command line again?
Yes.
So would it be possible, like, here's a path and argument, and just change it to like CGS?
No, but you can very easily extend the example to make this possible.
So I guess plotting z = 0 is
Yes, by default, it's plotting on the y plane. So
z = 0. Right?
yes, z = 0, but you can pass the plane variable to change the plane. But this, in this case, reads 2D data. So if you didn't output the plane that you want to plot, then you're not going to be able to plot that. But what I'm going to show you in a second is that kuibit can slice. If you have 3D data, you can get a 2D slice. If you have 2D data, you can get a 1D slice. So
in principle, you only have to output 3D data.
yes, but 3D data is much more expensive to work with. So if you plot the equatorial plane, just plot 2D data. That's much better. Yes.
Which tab is your iteration in your command line?
Where's so by default, the latest iteration is plotted, but you can pass iteration 0, for example. Iteration 0. And this will plot iteration 0. And I think I'm good. I don't remember if I'm going to show you, but it's very useful to know what iterations are available. So you can use the print available iterations, and you provide what variable you want to look at. And it tells you, okay, these are the iterations available for, in this case, since I want to give you the least amount of data possible, because GitHub has 50 megabyte limit, there's all the XY data.
Just a suggestion.
Yes.
I mean, for me, it would be nice if every single one of these scripts started with kuibit underscore, because otherwise it's kind of hard to like print available iterations.
Yes, well,
a kuibit.
Yes, okay, yes.
Yeah.
Makes sense. I also don't want to type every time.
Right, yeah.
And I like the tab completion.
Yeah, alternatively, you could just say kuibit space and then it could populate with plot or whatever.
Yes. But again, I don't call these are examples. You can do whatever you want to with these examples. You can change all the names and put kuibit if you want to.
Yeah, I forget that these are not like
I'm
supposed to keep using this.
No, you can use them, but okay. So as I try to emphasize, there can be lots and lots of options. So second way in which you can provide all these flags is providing config files. So here, instead of passing a -- variable row b, I just list everything I want. And I say, okay, I want verbose, I want a log scale, I want color, I want iteration 0. I want to show if I'm a level. If I'm level show, maybe. Let's see. And then it's plot grid var. And then you pass -c. Oh, actually, I already had that. Okay. This -c plot rowb.conf takes this config file and sets all these variables. This is very useful if you run the same script multiple times. So you just put all the configs there, and you run it. Say you have 20 simulations, you have the same config, and you don't have to. You just change one line, and you can script more easily your analysis. Maybe you put at the end of your submission file. And in this command, I'm also showing two other important concepts: this data dir and out dir. So data dir is the directory where you want to look for your simulation output. By default, kuibit looks at the current directory where you're running the script. And in this case, there's only the simulation data, there's only this tiny DNS. But if you run your script from somewhere else, then maybe you want to specify exactly where to look for data. And this is also useful if you're using the same factory, you have many outputs, and you just want to look at the last one, because the less data you have to process, the faster kuibit is. So maybe here you can pass tinydns/output 001, 0002, and so on to speed up a little bit. Yeah.
So I might have missed this, but
Yeah.
resolution is in DPI or is in pixels?
As in points, as in so kuibit takes your hierarchical grid data and says, okay, from -20, from x0 to x1, I'm going to put 300 points. Then matplotlib is going to put whatever resolution matplotlib wants to put there in terms of DPI.
Okay. So at the end of the day, it's working on 300 by 300 points here.
Yes, but what you can do is, for example, if you use imshow or whatever, you can tell matplotlib to use matplotlib's interpolation functions like bicubic to smooth that out. So yes, at the end it's working on 300 times 300. Yes. Cool. Okay. Whereas out there is where to save the artifact. In this case, it's a plot. In this case, I'm going to save it in TMP. And as you see, I'm mixing my config file with other options. This is perfectly allowed. There's even some options that you can set as an environmental variable. For example, I always produce plots in PDF. So I have a line in my config, in my bash RC that says kuibit, whatever flag sets in PDF. So I don't have to specify the extension every time. So if we plot this, and I'm also plotting refinement levels, that's just to show you that you can do it. Yes?
So is there something like a global config file as well, or is that all?
No, there's no global config file.
But they all start with kuibit.
So let's have a look.
The environment.
Yes, yes. So if you want to know which variables okay, actually, let me tell you, this is an example. So I'm showing you what you can do. In this example, I choose to make fig extension available with the end variable kbit_fig extension. So if you set that environmental variable, then this flag is automatically set to whatever you choose, unless you change it with the flag via command line. But again, you don't have to use this.
So that's basically what's implemented in the script and not by the kuibit library.
Correct. Yes. There was another question? No. Okay. So let's have a look at our TMP folder. We had a PNG. And now you can maybe see that there's one single refinement level, and you can probably guess that this simulation was not particularly high resolution. But if we were to plot more, you will see the entire grid structure. Okay. Let's see what else I have to show you.
So there already it's doing when you do the final level show, it's drawing the box where
yes.
the box was,
yes.
but it's still using uniform data.
Yes, correct. Okay, I've shown you this. Something that I find quite cute is plotting more complex variables. So, for example, let's say that you want to plot, well, my favorite example, that is the cold pressure for our simulation. In this case is the density times our polytropic index, which in this case is 4/3, 1.33. And just to show I'm taking the log scale. Here you can put any type of expression that you want. kuibit is going to parse. You can mismatch multiple functions like P. If P is the name of the grid var in your Cactus simulation, you can use it. And with this, you can just plot this, let's say complex object in the same way you plot a grid variable, but this is not a grid variable. This is like a derived quantity. So you can do some basic analysis involving even multiple grid functions without writing any code. And again, we can look at this, and this is what it looks like. This is very similar to our density, but this is our cold pressure. So we can probably take the ratio and see what happens, but I'm not going to do it because I didn't try it, and maybe it doesn't work. Yes.
So can you output color bar or color maps that are non-square?
Yes, let's see. This I can try. Let's see, minus 30. Yep. But again, you can look at the code and you can change it. So this is
So here's the question.
Yep.
Which direction had the 500 points?
Both.
Oh, interesting. So these are little rectangles we're seeing.
Yes.
Interesting.
That the resolution in Y is going to be smaller.
Yeah, the effective resolution. Yes. Okay. Well, let's.
A very short question.
Yes.
To go, so I want to ask you, this is really cool. Would it possible because Java fundamentally as also like HTML, it's mostly you use like HTML5. It wouldn't be too hard to add an additional reader and then you might.
So as it stands right now, kuibit fundamentally, when it comes to read data, had to re-implement carpet almost from scratch to understand what's in the HTML5 because Cactus doesn't really output HTML5. It's a really it's a Cactus specific format or carpet specific format. So I don't think it will be if you have this type of like hierarchy, maybe you can do something, but it wouldn't be like a natural choice to do.
I see. Okay.
There's some fundamental,
It could support it. It's pretty hard. I guess it could support the principle, but it would be pretty hard.
Yes.
So similar questions, but since Carpet X kind of has the same type of
Yes.
and there is an open PMD API
Yes.
system Python reader, how much confined to particular regions is this requirement about Carpet? They all have block structure being all the same.
Yes, so you have to. I mean, it's possible, but as long as this abstraction of like hierarchical grid data in which you can put like refinement level inside multiple components, as long as that holds, you can extend it.
You should be able to do geometry.
Okay. Yeah. I was wrong. Well, I have more examples. But then maybe I can show you. I don't know, well, let's just run them quickly so that I can go to the more interesting part. Let's look at gravitational waves. You're employing the gravitational wave stream, which is computed with the fixed frequency integration method for multiple moment L equals 2, multiple moment M equals 2. And here we're choosing our first detector in our series of multiple detectors that we placed. And this is going to look like something terrible because the simulation was very short. So
what's pcut?
Yes, so pcut is a parameter that you provide to the fixed frequency integration method. It's essentially the longest physical period in your simulation.
So it's in units of period.
P is period, yes.
Okay, gotcha.
Yes,
I'm just used to being in terms of omega or something.
Yes, but
sounds a lot more natural.
Yes, to me, it's very easy to compute the period of a binary as opposed to the frequency.
And can you sum modes?
Yes, you can sum modes, but if you sum modes, you have to specify where you're looking at because you have to convolve with the spherical harmonic, spheroidal harmonic, I think, if I remember well. So you have to provide our AM deck if you want to sum modes. Well, as mentioned, you can take slices if you don't have data. You can plot multiple variables. You're plotting on the x-axis, I'm plotting multiple variables. And clear, I have a future warning about something I didn't change. And here we have our constraints. Like I took a bunch of variables and plot them. Yeah.
Why do you always multiply the strain by R?
The strain, because R times H is units of M, so you can scale it easily. So you can easily choose, for example, if I want to have like a distance of 150 megaparsec, and easily rescale that. H otherwise is it doesn't have units, I think. Yes. Plotting energy, plotting time series. Let's plot a time series. I'm always speaking density because I don't have too much data in here, but so let's see pro maximum So once again, I think this is one of the most useful and simple things that you can want to do. You want to see the central density or your maximum energy. And here, I don't have to worry about all the restarts. I don't have to worry about putting together my files. I just run it. Yes. So the way gravitational waves are extracted is there's a thorn called multiple. The multiple thorn takes a number of extraction radii and decomposes psi4 on the various extraction radii. And detector number is the second extraction rate. Number 1, because it starts from 0, will be the second extraction radii that you define in your core file. Okay. Well, there's a bunch of scripts. You can have a look, the ones that are interesting to you. But I want to show you something more about movies. So with motion picture. So motion picture is another Python package that what it does, it abstracts away, again, this idea of like simplifying, takes away all the details that have to do with making a movie and just lets you focus on making one single frame. And I want to give an example of how to make this, but let's just run it to see what it looks like. So the way it works is that you have this code MOPI, stands for motion picture. You provide what I call movie file, which by default is motion pictures trying to find this movie file in the MOPI movie steer environmental variable. But if you don't have that, you can specify with this movie steer. You say, okay, look for the movie file here. And then if you look, it's pretty much the same as your grid bar that we had before. So variable, one log scale, one this resolution. Here I'm specifying what is the range I want to plot. So between -10 and -3, that is in log scale. Then I have this parallel flag, which means use all the cores I have on this computer. And for each core, process a different frame. I have this output file, output there, movie. And then in this case, I have a pickle file. I will probably discuss this a little bit later, but it's not needed. It's here just to make things a little bit faster. And I can run this.
Sorry, what is the first argument? The grid bar.
So the grid bar is the name of the movie that you want to make. So it's what you find in the movie steer when you download the Untitled token. The example, so there's a MOPI movies, and that's your essentially it's your script. It's the name of the script. Or let me remove
Video already exists.
Yes. Okay. Let's see if this works. Okay. So as you see, we have our verbose output because I like to know what's going on. So as you can see, we see the progress of frames being built. Question?
Yeah, so I'm really curious about this parallel option.
Yeah.
How are you doing that behind the scenes in Python? Are you
Yes.
using the multi-processing?
Yes,
network?
it's using multiprocessing. And
So you have multiple Python instances running right now?
yes.
Cool.
So yeah.
And it just automatically fills the number of cores?
Yes, unless you specify how many workers you want to have. There's more, you can specify how much work to give each worker. And this is useful. I introduced this to run on login nodes and supercomputers. So I can run like 2-4 nodes, 2-4 cores without destroying everything.
Did you make MOPI yours?
Yes. So this is running. As we can see,
Oh, and what do you use for the task, the progress bar?
so it's called TQDM. It's a Python package. Or my high CPU usage. Okay. Zoom says that the high CPU usage is affecting the meeting quality. So let's wait for 25 more seconds. Hopefully Zoom doesn't crash.
The thing is that people still be able to hear you because you're not using like this.
No,
The microphone is here.
Yes. But I still want you to be able to see what I'm doing. Okay. So 6. Okay, so animating frames. It behind the scene is using FFmpeg, and we can run this, and we get our binary. I'm sorry for the. So on my computer is running perfectly well. It's not choppy. If you don't believe it, you can see it's working well.
Oh, beautiful.
So again, the idea here is that we didn't write any line of code, and you are able to make a movie of any grid variable that you want. So Yeah, it's getting better. And we can, with motion picture, there's a billion options as well. You can change like frame rate, you can change what frames you want to look at, you can change extension, like you want to use MP4, you want to use MKB, everything is taken care of for you. So you can just focus on your plotting. Okay, so this was my part 2 or 3, I don't remember. I probably skipped something, but I think you get the gist. But I would like to move to the next part in which we do some collaborative live coding, possibly. But if people want to take a small break, people want to ask questions, I think we've been going for 60 minutes at this point, I don't know, 55. So it's probably reasonable to take questions or break, yes.
So you're showing like examples with a very small file.
Yes.
But if you have like a production run with 7 refinement levels with a huge grid, that, 2 terabytes.
Yes.
How well does this scale?
Yeah. That's a very, very good question. So I've used this. I've made movies of like something that was order of terabytes, but you cannot just plug and play. You have to like extract, for example, only the iterations you're interested in, or only the variable that you're interested in, so that kuibit doesn't scan like 2 terabytes.
Okay.
So there is some workarounds. There's something is in the documentation how to speed up some things. It's possible, but you cannot, like this will crash before a 2 terabyte simulation.
Yeah, I guess my second question would be when kuibit looks at like an HDF5 file,
Yes.
does it process the entire file, or does it just look at the metadata?
Yes.
And say, okay,
So it depends on how you output the HDF5 file. So kuibit doesn't. So for if you were to look at an ASCII file, kuibit has to read the entire ASCII file. So it can read the 3D ASCII file, but they will take forever. For HDF5 files, I can ask for the metadata and get a sense of what's going on by looking at the metadata only. But sometimes I have to do more. If you don't remember, if you output like multiple variables per file, then I have to open each single file. This on some file systems is very expensive. So from some file, for some files, I can get the content from the name, like I don't know, bx.xyz. So, but in other instances, I have to open the file. So depending on, yes, for example, that I think so.
Okay.
I still don't read the entirety of the file. So if it's 2 terabyte, it's still going to be reasonably fast, but it can be slow, like depending on the file system, because you can have like thousands and thousands of files. Which brings me, it's a good point to talk about this pickle file. So one of the most expensive operations is just to understand what's inside your simulation, because I have to open thousands and thousands and thousands of files. If you output multiple moments in ASCII files, like say that you output up to L equals 8, that's like 500 files per, 8 times, I don't know, but like hundreds of files per output folder. So if you have like 50 output folders, that's like several thousands of files that I have to open each single one to understand what's inside. So it takes a very long time. So this pickle is, okay, I've done all the work to understand what's inside my simulation, let's save that. So when you run the first time and you understand what's inside, you can save the output to a pickle file and you can restart from there.
You got to be careful with pickles.
Yes.
They're not version.
I'm very familiar. If you open the documentation, it says,
unlike their name,
yes,
they don't preserve stuff.
I'm very, very familiar with that. And so you have to be careful. I perfectly agree. But that's the best way I found to, speed up
an individual.
Yes.
So what's in the pickle is you also pickle, say, if I want iteration blah.
So initially I tried that, but then the pickle became gigabytes,
Yes.
so it's pointless. So I pickle only essentially like the metadata. So it would be very nice if carpet text or whatever had a like machine readable metadata. Yes. Yeah. I know. Yes. So there's a lot of work that needs to be done to just understand what's inside the simulation.
I am curious why it takes so long to read an ASCII, because there are different ways. I don't know if you're familiar with the different ways in Python you can read an ASCII.
Yes.
Some are much faster, like order of magnitude faster than others.
Yes.
Are you trying like the best practices kind of?
I think so, but I just think there's so many, and
it is a big file.
And
they do get large.
It's not the size, because sometimes I just read 10 lines, I just need the header. But there's so many that the file system is often the problem.
File system.
Yes. like we're talking about thousands and thousands of files for any simulation. So just opening it takes a little bit.
As an example, so on the waters, we had a very strong recommendation. Don't put more than 1,000 files at most in a single directory. Even with those numbers, it might usually take you 5 seconds just to open the file. Not reading it out. The open call takes 5 seconds. Because Lustre doesn't like thousands.
So yeah, so they're very small performance. Like to me, the biggest performance gain was more from asking multiple data to HDF multiple data, which moves from thousands of files to one file. That saves so much time.
I had to do that for my run last year where I was talking hundreds of simulations and ended up crashing our file system because I got on order of the files.
Yes.
Switched to HDF5 and trimmed it down. Hey, my thinking was a little bit slow, but yeah, I mean it's a huge strain on the file system.
Yeah.
It only gets amplified when you start going to files.
Which I can say what is one trick to improve performance. If you just want to plot the density, create sim links to a different directory that links only the files that contain the density, so that kuibit only have to scan those files instead of scanning the word. So that's one trick to reduce from 2 terabytes to 500 gigabytes, for example.
So I guess what I'm going to say now is going to hurt your heart because I guess that's exactly what you wrote this for. But when we try to make movies from simulation data, basically what we do is you run a script that scans the ASCII file, like looking at chunks at a time.
I know.
And then interpolates it to a uniform grid, which I guess is what you do with just one command. And then we plot from that.
Yes.
So while it might seem clunky, it allows us to read these gigantic files on a laptop if I have to. Like, can you do that? If I put a 2 terabyte, I mean, I can't even fit that in this laptop. But if I had a 2 terabyte file with good qubit process.
Yeah, well, I would say so, yes. I think
it doesn't have, so it's more like in this sense that it doesn't have to read the entire file.
Yeah, no, it doesn't have to. No. Unless it's an ASCII file that you have. Okay, no, yeah, so you want to read sections? No, you have to read entire.
So it would have to be like an HDF file.
Yes.
There's probably also a question for the ASCII file, you scan through it, but you're not keeping the content in memory.
Exactly.
Right? So you always, you read through it once, and then if you want to plot something, you still will read only whatever the 6,000 lines you need, which might still be big. But...
No, so the way, okay, I don't want people to use ASCII files. So, the way ASCII files is implemented right now, I think, if I remember well, is that I go line by line to understand, read line by line to understand what I'm plotting, and I'm constructing like dictionaries with I don't know, like what variables are available, what iterations are available, the size, because maybe you change your your simulation grid at some point, and things change. So I cannot assume.
You can't
I have to
just for
read
the first time what it is.
So that's why ASCII files have to read everything. And in 2D is doable. In 3D, no. But it.
2 terabyte ASCII file, we're doing something wrong.
No, yeah. I'll give it an extreme example.
Okay. So now I think we took a break, so we can move to doing something that is not ready-made, so that you can see, how I approach the problem. And again, ask questions, make comments, ask me. So what I'm going to do is I'm going to make a script that plots vector field lines. So at the moment, this is not available in kuibit. And the reason it's not available is not because it's hard, but because it's very hard to make it general. I want the script to look good, the output to look good for every single possible configuration that you have. And this, I couldn't get it to work nicely. Sometimes the field lines just suck. So that's why it's not available in kuibit, at the moment at least. But if you want to do it yourself, it's not terribly hard. So let's try to do that. So I'm going to create a file vec.py. So I'm going to have, so here I have a Python shell, and on top I have my file. So let's save this. So first step is always to import simdir. So simdir, import from import is the main reader. Simdir is what is your first point of entry in your simulation output. So we can have a sim, and we provide the folder that we want to where our output lives. So this is your top level directory. If you have your output 00, 001, this is your top level. And okay, if you don't know any better, you can always print, and we can see what's inside. So in this case, we have some gravitational wave data, we have our constraints, we have some grid data, and I chose to have a Vx and Vy so that we can plot vector field lines. Okay, so this is what's sim there. So let's continue. Next, we want to work with grid functions. So of course, our first grid functions is going to be our density. So if we want to read density, well, we want to start from sim, then we want our grid functions. So as I say, we have a lot of suggestions. We want grid functions. Actually, let's do one step at a time. So what is sim grid functions? Well, I don't know. So let's print it. Well, sim grid function just contains all the grid functions that are available. So okay, we have 1D grid function on the x-axis. This is what we have. 2D grid functions on the x-y axis. This is what we have. So now that we know what we have, we can focus on the xy plane. And I say, okay, on the xy plane, this is what we have. And again, when you're lost, you can ask for what type is this object. Well, this is all grid functions. So this is a reader, and the all in front tells me that the keys of this object are variables, and you can ask with keys. Oh, nice. Okay. This type. Okay, print. So these are the keys of my object. So this is a dictionary-like object. So what we can do is we can just ask, okay, I want row B. I think, okay, it doesn't print. Oh, so let's keep. Okay. So this is a one grid function. So this is not yet our data. This is a reader for HDF5. We can see from the H5 for HDF5 files that contain this grid function. And we can see, for example, available iterations. This is the iterations that we have across the entire simulation. And here, as you see, we don't have to worry about reading a file. We don't have to worry about where the file is. We don't have to worry about which file we're looking at. It just works. So let's say that we want iteration 0. Okay. So as you can see, now we have a bunch of refinement levels. You can see what is the dx of highest refinement level, the lowest refinement level. Yes.
Is there an equivalent command, available times?
I think so, but available times is much more expensive. Typically, because while I can get the iterations from the keys in the HTML files, I have to read the HTML files to get the times, because the times is one of the metadata in the HTML file. So if you can, use the iterations. Also because they're integers, so there's no floating point issues.
And I think every time you want to access something, you're going to have to use the iteration anyway. It's not time.
Yes, in most cases, things are indexed by iterations because floating points are not hashable. You cannot put them as keys of dictionaries, whereas iterations are. So yes. But as we saw, maybe type. This is our favorite. Oh, forgot this here. Is hierarchical grid data.
Is there a way we can know the meter steps? Which steps are meter steps?
The what? Sorry.
Like the meter steps. So basically, when you have a plot or a tree,
yes.
Not only scale they have to be the your own output every secret, like coloring output every something.
Yeah, you can change the iterations, but you still have, if you work with iterations, everything will work better than working with time steps because of the way things are saved. So you can change the frequencies as you want, but when you read stuff, iterations are better for technical reasons. I can go into details, but you can trust me, or we can start with it. Okay, so here I think we can get, for example, this once again behave like a dictionary. So we can probably get the first type, the first refinement level, or if we want. This is a list because typically you can have multiple components at each refinement level. If we pick the 0th component, this is the uniform grid data. So this is the data at iteration level 0. And if you want this as an NumPy array, you can add this dot data, and this is an NumPy array. So if you really want to get down and work with them with NumPy arrays. So this is how the code is structured. So this is how this object behaves. You have all these levels of.
So once again, the first 0 is the time. Second 0 is the refinement.
Yeah.
And the third 0 is the component.
Yeah.
Of the refinement.
Correct. Yes. And
To merge them.
yes, if there's multiple components and they form a single patch, everything is merged together for ease of computation. The fewer components you have, the faster things are because you have to iterate over. Question? Okay, so maybe we can start writing something in our file. So from same there, import same there, same. Okay, so let's say that we want iteration 0. So our row B is going to be same the with functions, which you can, I think you can shorten with GF or GFs, the same. And let me show you a different way to access data. So you can do fields, so row B, and we want iteration. Okay, so let's evaluate this. So row B. Okay, so row B is there our hierarchical data. So here I sent my code from here to here. Okay, so now we have our hierarchical grid data. Once again, if we want to do plotting, we have to resample. So let's say that we want to resample from -30, -30, 30, 30, and we want 10 other points. So resample can be, you can use unif row B to uniform grid data, and we provide what I call shape. So shape is the number of points that you want to use. So in this case, it's 300, 300. You provide the lower corner, what I call x0, and the top corner, which is x1. So let's see if this works. Once again, I send the code from the top to the bottom, and let's see if we have our B unif. Yeah, this is a uniform grid data. So now we took all the information that was in all the refinement levels. We used the best information we could use, and we are sampled to a small grid that has 300 times 300 points in the region 30, 30. And okay, let's plot this. Let's use kuibit for plotting. So from kuibit, visualize matplotlib, import plot color. So plot color is super powerful. Whatever you give plot color, it will work. You can plot NumPy array, you can plot hierarchical grid data. If you provide enough argument, it will plot something. In this case, we can just plot color row B unif. And so this plots and uses matplotlib. Somehow we have to save or show this plot. So we have to import matplotlib as well. Import matplotlib by plot. And we can, I don't know, save it PLT or show. Let's see if this works. So I'm going to evaluate this code. Let's see what happens. Yep. So here we plot our grid data. We don't like this because when we work with density, we typically prefer log scale. And maybe we also want to add a color bar. And maybe we want to add some labels. I don't know. But this, actually, let's do this. PLT dot X label. This is your usual matplotlib. You can use matplotlib, whatever you know about matplotlib, you can use it here. X. So since I'm working the same session, I need to clear the figure. So let's run this again. Now it's running. And here we have our figure. So as you see, there's an X here because we put that. Then I really don't like the defaults in matplotlib. So since I built kuibit, I built it with my opinions. So there's a setup matplotlib. So what this code does is set up matplotlib with my favorite options. But here, if you put any, I don't know, I don't even know, fixed size, whatever. If you put any configuration in matplotlib, this function is going to update the matplotlib defaults with the configs. But by default, it uses my favorite configs. So if you do so, and you run this, right, you get much more readable labels instead of like tiny stuff. Better color map in my opinion, but this is just my personal choice. Okay, so now we have the density. You know, in simulations, typically we don't really trust. Yeah.
Just a quick question about the color bar.
Yep.
So how is it finding the limits to put on there?
Okay, so you can provide your own limits with vmin vmax, vmin -6 vmax equal 2, whatever. Or I think by default it takes maximum minimum, or I think maximum minimum probably, yes. But we can try this. Let's see if it works. I'm running this.
What does it use under the hood to generate the block? Is it in show or is it?
Yeah, so when you use block color, it's imshow, but you can put like contours. Well, if you do block contour F, then you block contours.
So they use like B color match.
No, I don't use B color match. It's imshow, or I think there's a block color contour F function as well. And visualize matplotlib, and this is a field contours of which can be useful. So yeah, so put in vmin and vmax set the limits, but I'm not going to do it here. But something I'm going to do is, typically we don't really trust. Actually, no. Let me plot first our vector field. So, well, we read and resampled our density. Let's do the same for our velocity fields. So I'm just going to copy and paste. And I just have to change this to Vx, Vy. I hope I'm probably going very fast. You can slow down the video later, or I hope what I'm doing makes sense. But Vx, Vx, Vy, Vy. Okay. Now we have our, when I evaluate this, we're going to have our data. Let's go remove this. Now I want to plot Vx and Vy as a vector field. So to do so, I'm going to use the function streamplot. So plt stream plot, and we can look at the documentation. Documentation says, okay, we want x, y, and we want uv. So we want the coordinate and we want our vector field. But this, of course, is not going to work with uniform grid data, because uniform grid data is something I define, and it doesn't really talk very well with matplotlib. So I mean, we can try, but it's not going to work. So I have to go down one level. I have to really use the data, and I show you how to access the data. The data is, if I look at row B unif, the data is just in .data. So this is an NumPy array. Let's make sure that this is the case. Yeah, this is an NumPy array. So this is how I move from this complex representation of all the hierarchical grid data with something that is not supported by kuibit, but you can do whatever you want with it. You can use you don't have to use matplotlib. You can use whatever you want. This is the basic fundamental building block that you would use. This is the data read interpolated on a grid that you define. So now we want the coordinates. So we want x and y, and we get them using Infer, the coordinates from grid function. So there's multiple coordinate functions. The one that we need now is coordinates from grid, because this returns NumPy arrays. If you were just to use the coordinates function, you get uniform grid data.
I have a question.
Yeah.
The x0 and the x1, you just hard coded those.
Yeah.
But could you get those from row B itself?
Yes, you can get them from row B, and you will plot the entirety of the thing. But these simulations have a ton of like nothing. Yeah. You can. I think. Let's see. Row B is probably x0. Let's see if it works. Yeah, this is the x0.
Okay.
So now I have my x and y. Let's evaluate this. X. This is an NumPy array. So now I'm almost ready. Actually, stream plot 1x, 1y, 1vx unif. And we said that with one NumPy array we want data, y, unif, and one data. And I think we can plot this. But I think I need to change the color, and you'll see why. No. Oh, well, let me change the color. Okay, I sent this. I think. Yeah. Oh, this doesn't make sense. Why? Clearly, there's something wrong. And so what's going on here? It's interesting. That is the convention between Cactus, Carpet, and NumPy on how to lay out the data in memory is different. One uses C, the other uses Fortran. So there's a transpose in between. So we can just transpose the data. Or if you want to plot, you can use this XYZ, which is just an alias for transpose, which is a little bit more readable to me. So now, if I run this again, we should get our vector fields. But we can do even better. What we can do is, we have a ton of like black, yes?
So looking at what you have right now, so your X's and Y's, they were already in the matplotlib column order rather than Cactus row major order?
So I think there's a billion different coordinates problem. And I think by default, actually, I think X is a linear NumPy array. So there's no ordering.
Oh, because it's just, okay, it's just linear.
Yes, but you can get different. There's multiple options on how to get the order. You can see look at documentation for that. Okay, so what I wanted to emphasize that there's a ton of black in our figure that we don't really want. The atmosphere, we don't care about the atmosphere. We don't trust the atmosphere. So let's remove that. So to remove the atmosphere, we can apply a mask. So I can take my Ruby and I can mask less, I think, is it? Unif. Will be unif mask. Yeah, mask less, and yeah, I'm looking at this up here. Row atmosphere, which is something I am going to define here, and let's pick 1 to the -8. Okay, let's run this again. So now, if I did things right, here what I'm doing is I'm editing an object in place. So kuibit uses this convention. Okay, so we remove the atmosphere. So the real color I wanted was black here. Kuibit uses this convention that imperative verbs mean edit the object in place, whereas past tense means return a new object. So now I can take my mask that I applied, that I constructed with my density, and I'm going to apply to my velocity fields, so that I don't get spurious information from the atmosphere. So I'm going to show you the example with unif. Now it's, I think, applied mask. Let's see, or mask applied. Yep, and I'm going to use row b unif of mask. So what I'm doing here, I'm getting the mask information from my density and I'm applying the mask on my velocity. So here I'm going to do uy unif maskless dot mask. Okay. Now, and I think let's run this. Let's see if this runs.
Will be unit max.
Yeah,
10 to the -8.
Who cares?
It's 10 to the -8, yes. So I remove everything that's below 10 to the -8.
But that object there.
Dot mask is essentially is the mask that you obtain when you apply the less than to the row b. So essentially I'm constructing and getting information from the density. I'm constructing a mask from the density, but I'm applying that mask to the velocity because I don't want to mask using values from the velocity. I want to use mask using values from the density. Okay, so something, Phil?
And mask less.
That's why. Yeah, mask less is yes. Sorry. Yes, I
okay. The first one you used like a float, and now you're using an object.
Yeah. So here I'm showing two different ways to obtain the same result. In one case, we have that I use the method return something new. That is an object. No, because the bus. You're right. Is it? You're right. Let's see if it works. Yeah. Otherwise, I just throw away the result, which is not what I want. Yeah. Okay. So now that we have that, maybe I can take questions. And then what I want to show you is how you can transform this into a movie in 5 lines.
So if everything we did, we still only have something like 3 arrows in our stars.
Yeah.
There's only 3 points in there, or
No, because that's a vector field. I don't know how you probably can customize with this plot stream plot.
It doesn't use the mask to construct more points in that.
No, so what it did, it ignores all the points that are in the atmosphere. We still have 3 because the information in the atmosphere, the velocity was 0 because it's iteration 0. So there was no field line there. So it doesn't really make a difference at this iteration. We can probably try with some other iteration, but I'm going to do something else instead. I'm going to use motion picture to transfer this into a movie. Because now I want to show you, I want to emphasize how we had some configuration here. We had some setup here. And we had some plotting something here. This is what motion picture wants. It wants some setup, wants some plotting. And the missing piece of information here is it wants what is frame. Motion picture doesn't know what is a frame. By the way, motion picture is completely independent of kuibit. You can, if you want to make any type of plot movie, you can use motion picture. Let's see, I think I have, it's on GitHub. There's probably some examples in which you can see like unveiling and sine wave in here. So what you have to provide is some initialization, how to define a frame and how to make a frame. So let's do this. Let's transform our single frame, single plot into a full movie. So for that, we have to, so motion picture uses object-oriented paradigm. It defines an object that has to be called multi-movie, and it initialize an object like this, and it works. So let's take inspiration from this. Let's maybe copy this, call this vec movie. Pi. We save this. Oh, I pasted this. Okay, now I need class multi movie. I need an init. So the init can optionally take arguments, but I don't think I need any arguments. So I'm going to just say that I don't need anything. And then I have this. I need this. Do we have 8? Check. 3, 4, 1, 2, 3, 4. Perfect. And I need this. Okay. So this is the information I have to read once and never more. And I think it's useful to use a pickle file here. So let's put it. Everything will work without it, but it will, since Zoom is training my CPU, it's better to put it here. Then we need to specify what is a frame. So motion picture doesn't know what is a frame. If you want to index frames with iteration, you can do it. If you want to frame index frames with time steps, you can do it. If you want to frame with, I don't know, the years in which Italy won the soccer World Cup, you can do it. So this get frames is a function that returns an iterable, typically a list with all the frames available. And the frames that we want are the iterations, so our available iterations. Or actually, I don't have to read the iteration, this is wrong. Okay, and finally, I have to specify how to make a frame. So make frame. Thanks. Make frame takes the place where you're going to save the frame, so path, takes what is a frame, which in our case is going to be iteration, but it can be whatever you want. So frame number. And here is just your usual matplotlib code to plot a single frame. So what we want is we first want to clear up what we had, and we want to probably set up matplotlib. We want this, but we have to read the frame. So here there is our frame number. Oh, sorry if I'm jumping. I hope you get a sense of what I'm doing. I'm porting the code so that now all the plotting happens in this function. But I changed what is the definition of row B. So the row B contains all the frames. It's our one grid function H5. So I have to read the specific iteration. Then I'm going to read, thanks. I'm going to apply our masks. I'm going to plot. I'm going to read my coordinates. I'm going to plot. Instead of show, I'm going to save fig to my path. I think this will work. So finger crossed. So what are we going to do is we're going to use Mopi. Let's see, probably -1. No. Okay, no. Vec movie. Actually, let's do this Mopi. Help. So when you do Mopi, okay. So help tells you which movies were found in your Mopi movies here, which in this case is the current directory. And these are my 2 tests that are in the repo. The one that we just made is this vec movie.py. So I can just pass, I think, vec movie.py and probably parallel. And probably we want to put in movie 2. Let's see if this works. Variables. Okay. Oh, okay. I know what's going on. So yeah, I forgot. So what I'm doing here, I'm saving all just these objects in my object. So this doesn't make sense. This is Python object-oriented stuff. So self. And I want less. Okay. Let's see if this works now. Okay, I forgot again Ruby. Where did I forget Ruby? I know, it's here. Something is happening. So let's see. So if it doesn't work, I'm going to pull the correct solution from my, okay, well, something is running. It's going to take 6 minutes apparently. But in the meantime, we can check out if something is being created in movie 2. Yeah, well, that's what we had. Let's see if we have a second. Okay, something is moving. Okay. Well, in the meantime, so apparently we have 3 minutes for some questions, or yeah?
Yeah, okay, so, I mean, it sounds like you understand a lot of the performance bottlenecks when it comes to reading the HTML5 file. Sometimes you have to go through the whole darn thing, and sometimes it's in metadata, and you just read it once and you're good. I'm curious if you've thought about some of the optimizations that might be there if, for example, you created some C bindings or something like that. Or have you done that already?
Yes. So yeah. So well, as we discussed, well, it depends on what you're trying to do. If you're trying, in most cases, a main bottleneck is again looking at your directory, understanding what's inside. I don't think you can get speed up that in any meaningful way because the bottleneck is the IO. Is how your file system gives you the HTML file. And on supercomputers, this can be very, very slow. It's not a CPU bound, but in other cases, it is CPU bound. For example, when you're doing resampling, it's not. I wanted to make sure that everything was general, so it's not super well optimized. So it's Python, and it can be slow. So if you're resampling, then it works one point at a time. If you're resampling, then it will benefit from some like C Fortran, backend or Python or whatever. And instead of working one point at a time, it works with all the points at the same time. So these are 2 ways to improve things.
10 minutes.
Is any of the file system overhead unnecessary? Like, have you thought about?
Yes. So if
Like minimizing.
Yes.
Something, I mean,
Yes.
would it require lowering the feature set, for example, right? Because it looks like if it's scanning through an entire directory, it doesn't sound like it necessarily needs to, because if you're a user, you already have in mind, well, I want to plot the density.
yes,
I don't need to scan through the velocity file.
yeah. So that's why I didn't implement anything. I have a workaround that is, if you know that you want to work with gravitational wave data, you don't care about anything else. What I recommend you do, if you look at the documentation and the frequently asked question, which is a question I ask myself, but I can share, is how to speed this up. You create a new folder. You symlink all the files that you want to use in that folder, and you use that as your data data. So all the other files don't have to be scanned. It's much faster. But the other alternative is you just scan everything once. If you know that you want to do analysis and you're done with your simulation, scan everything once, save in a pickle, and you don't have to do anything more. So that's the other one.
Oh, okay. So you're scanning. Okay.
So there's
the scan is in the or in the
yes. And there's a example called Picklify. What Picklify does, it scans everything and saves in a pickle. And so you don't have to do it. You just Picklify.
Just do it once.
Yes. But you have to be careful, as I say, because if you add a new checkpoint, then you're not going to see that in your pickle, because
You have to rescan.
you have to rescan. And yes, so this worked. Okay, we can keep our finger crossed. So it was movie 2. Oops, sorry. And we get our vector field.
Oh, with your laptop. Yeah.
Oh, ours is not yet. We're gonna be sure.
Okay, so camera can record the laptop there.
If it gets swirled, I can.
Yeah, so okay, so in these final minutes, I'm going to show you one last quick thing, and then hopefully more discussion if you want, or it's already late. You bear with me for 2 hours, so we can have dinner. So what I want to show you is, well, here we've done the minimum amount of work to achieve this result. But I think the real power here is that we can remove all these hard-coded values here. What if we make them command line accessible? What if instead of having a script that works only for tiny BNS, we have something that works for everything? This is exactly what examples are. I'm using argparse, this library in Python, to set everything from command line. And there's some helper scripts to help you doing that. So that instead of having all these hard-coded values, everything is general. You can put your script in your path and you can use it for any single simulation that you run. But even better, you can share with other people. So anyone can use it for any of their simulations. Kuibit, I've abstracted away all the details. This will work. In most cases, it will just work for everyone. And similarly, for movies. So here we have our movie. So this is the larger version, in which that I wrote, in which we have an additional function for motion picture that's called multi-add custom options. So these are all the options that the movie file will take. So as you can see, we have this KAH is a kuibit argparse helper. So there's some ways to add some features already. For example, if you work with horizons, you can just hide horizons to parsers. So you have all the interesting stuff about horizons. So here I'm passing all the options that I want to be command line adjustable. And I just have to do a little bit more bookkeeping around here, because I cannot give things for granted. For example, I don't know, like I'm not assuming that I work with the XY plane. Maybe I work with the XZ plane. So there's a little bit more work to do. But this entire file is 200 lines, and most of it, all these lines are not like super meaningful. It's just this line contains 3 letters. So this is not super dense, I hope. It should be relatively straightforward. We're doing the same. We're reading the variable, we're sampling the variable, we're applying the mask. There's just a bunch of phase statements because I want them to be runtime adjustable. If we want log scale, if we don't want log scale. But with this, we wrote, again, a movie in less than 30 minutes for plotting any type of vector field or any type of variable, as long as it's a vector.
5 minutes.
that you can use and you can share with your friends and you can share with everyone, and it will just, again, it should just work. So yeah, I think this is what I want to show you, and yeah, thanks.
So I have, I mean, the elephant in the room is carpet eggs.
Yes.
And so can you comment on your progress with that?
Yes.
Has the data format even been finalized for HDF5? No.
Oh, no, first of all, it's not HDF5.
Oh, right, it's the
ADOS.
OpenPND, yes.
Yeah, so I had a discussion, let's say with Eric about this, and we try to understand if this can be adapted to CarpetX. But the main point is that if I don't use CarpetX, I'm not going to adapt this. So anyone is welcome to do whatever they want to adapt this to CarpetX. But if there's no use case for me for CarpetX at the moment, I'm not going to do that because it's not easy. It takes time, but it can be done. Like as long as there's Python binding, as long as there is a place where you can add a new reader for CapEx, and if the abstraction is still the same, this can be applied. So yeah, that's the state of CapEx at the moment. Cool. More questions?
Yeah, it's probably a little soon. I'm sorry. It's probably a little soon to make the CarpetX one. CarpetX is still, I think, probably not flux.
Moving target.
Still a moving target.
Yeah, which brings me, so something that I think will be very cool to do, which is the first step I will take if I were to implement support for CarpetX. I would write a function that produces metadata read from carpet simulation in the CarpetX format. That is, CarpetX wants to have YAML with specific information. Instead of saving the information in a pickle, I want to save it in the same format the CarpetX wants. So this will bridge the two implementations and will speed up significantly the scanning process because it's no longer a pickle, but it's something that you can work with and edit.
Are there examples of how to read like a custom data file, for example?
A what?
A custom data file. Like if I wanted to write like a reader for volume integral.
So there's no examples. We can definitely discuss that. I can show you quickly where that will go. And I have 2 minutes. So kuibit. So I think that will go in probably Cactus scalars. So the convention is everything that starts with Cactus is something that's specific for Cactus. So it's not like an object. And I think there's a volume. Let's see, here. So as you see here, we have all the regular expression in which I match the file name, I match the reduction, I find if it's compressed or not compressed, I find the columns, I find the folder, all this stuff. So this is probably what you want to do. There's a lot of logic here to support all the different options that Cactus took it allow. And I shouldn't take credit for this because most of this comes from Wolfgang. It's re-implemented, but the fundamental ideas of the structure comes from Wolfgang's post-Cactus.
But a good place to start would be to like make a copy of this function and just adapt it.
Well, it depends. So if logically your file is like a time series, I would like your file to be indexed along with the other time series.
Yeah.
So probably it will be like a new reduction or something else.
That's more like time series.
But in other cases, example, the apparent horizon finder, it's a completely different beast. It's a completely different reader and I put in a completely different place.
So I think the work like if I want to listen for sometimes people have to set up with directory, right? And actually the kuibit can actually pick out all the directory and let's say I want to make a 2D like movie from the data from all 10 of the directory. Can they do that?
Yes, so you wouldn't do it. So if you just provide the top level directory that contains the 10,
30 seconds.
we will get confused because maybe you have density at the same iteration everywhere. So kuibit cannot index that. But you can you can specify your data dir for each single directory, and kuibit can make movies for every single one independently. More questions?
How does this for like distributed like
I've never used them, but you can run this with any, this is a script, you can do anything you want. Yeah, I think it is, I mean, it's not, as long as your operation is parallelizable, that is, you work with different iterations, you can work with distributed systems as well.
All right, well, thank you, Gabriele, once again, for that outstanding tutorial.